Okay, so for 3, 8, you first need to remember what a complex number is. So I think you know what that is. A complex number is just when you have like 3 plus I, that's a complex number. 2 plus 4i is a complex number. Even 2 plus 0i is a complex number. Complex just means in the form of a plus bi. Just lost my projector. That's not good. I think I pulled the plug on it by accident. Okay, so notice that 2 plus 0i is actually just 2. Okay? So what we're saying is that the real numbers, like 2 and 5 and stuff like that, are part of the complex family. Okay? How many of you knew that the rectangles are actually, the squares are actually in the rectangle family? How many of you knew that? Square is considered to be a rectangle. Some people even consider it a trapezoid, although I disagree. It is definitely, a square is definitely in the parallelogram family too, isn't it? Okay, so it makes sense to us to say things like 2 is a real number and it's part of the complex family. Does that make sense to you? Part of the complex family if the I part is 0. Okay. Write this on your paper, 0 plus 2i. 0 plus 2i. 0 plus 2i, of course, reduces to 2i, right? But 2i, even though it's purely imaginary, is part of the complex family. You want to write that? Okay, so here's what I wrote on my paper so far. I wrote 3 plus I, 2 plus 4i. Those are obvious examples. Then we have more interesting examples like 2 plus 0i, which is actually just a real number 2, and 0 plus 2i, which is just a purely imaginary 2i. All of these are in the complex family. Okay? It's like saying cats, dogs are in the mammal family, and so are humans. You know what I'm saying? So that's just kind of how the numbers work. This means that all the numbers you've ever seen in your life are complex numbers. Rad 3 is a real number, but that's a complex. Rad 17, that's a real number. It's in the complex family. I challenge you to come up with a number that's not in the real family or the imaginary family. We haven't even seen anything like that. Okay? All right, so complex kind of covers it all. Okay, let's go on and talk about graphs, though, because that's kind of where we started. So graphs, let's talk about the graph of y equals 5. That's a simple enough graph. Everybody sketch that with me. Y equals 5. Okay? Notice that this thing has degree 0. What does that mean? That means there's no x's, right? And if there are no x's, then that means the degree is 0. And notice how many x-intercepts it has. How many x-intercepts does it have? None, right? So we have a degree 0, and therefore no x-intercept. See that? Okay, that's interesting. In fact, there's no real solution at all. You cannot set 0 equal to 5 and get anything meaningful out of it. 0 equals 5 is nonsense. Right? You can't solve for where y is 0. It doesn't make sense. Not even in the imaginary world does this make sense. Okay, let's go on to the next one. A linear function of the form y equals mx plus b. So I'm talking about lines like this one, or maybe it's going down like this, but the slope is not 0. It says right here, the slope is not 0. What do you notice about these? This might be, for example, the line y equals x plus 2, and this might be the line y equals negative x plus 2. But what do you notice about both of them? How many x-intercepts do they have? 1, right. So the degree is 1, and there's 1 x-intercept. And there's one real solution. If you take 0 equals x plus 2 or 0 equals negative x plus 2, it gives you exactly one real answer. Okay, let's go on to the next case. By now you should know that the polynomial that is quadratic means degree 2. So I shouldn't even have to put that in parentheses for you. You should know that quadratic means degree 2. You should also know that the graph of a quadratic is a parabola. Okay, everybody should know that by now. I need to clear my ink. Can I do that? Okay. So, clearing the ink, and I just said that we're going to be drawing parabolas. Okay, you have a little bit less space than I do, so draw small. Let's say that your parabola factors into x minus 2x minus 5, right? The graph for that thing is going to basically pass through 2 and 5. It's going to look like this maybe. Oops. Something like that. Or maybe it's upside down and passes through 2 and 5. We don't know. But the point is it has two x-intercepts, right? 1 at 2, 1 at 5. Okay? So that would be a good thing to draw for our first bullet. Now what happens if your parabola is x minus 2, x minus 2? What would that look like? X minus 2, x minus 2. I know you have to draw very, very small here. Sorry about that. I'm trying to save the trees. Does it cross the x-axis? No, it touches the x-axis. Where? At 2, right. So we talked about how you can have a double root, and it provides us with a touch point, not a crossing point. But it's still a meaningful thing, isn't it? Now, let me ask you a question. How many x-intercepts do you see with your eyes in this newest picture? One. But how many real solutions are there to the problem? Technically 2. They just happen to be the same number. 2 and 2. There's still 2 answers. They just happen to be the same root. Okay? So we would still say that this is a 2 real 0 situation. So both of these diagrams go under your first bullet. Okay, I know the space is really small, but you need one picture like this and one like this. These both count as 2 real solutions, even though it appears there's only one here. These guys count as 2 real solutions. Okay? But when you graph it, of course, it looks like one solution, you know. That's kind of the way they look. Okay, let's go to the next case, 2 imaginary zeros. Let's say that you worked hard and you had this problem, x squared plus x plus 13, and you did the quadratic formula, you set this equal to 0, and you did x equals negative 1 plus or minus square root of b squared minus 4ac. Oh, okay, that's going to be 52 all over 2a. What are you going to do with this? 1 plus, negative 1 plus or minus I rad 51 all over 2. Hopefully last year you learned to separate that into a real part and an imaginary part. So the first part is negative half, and then you have plus I root 51 over 2 and minus I root 51 over 2. Notice that you have 2 imaginary answers. They're actually conjugates of one another. One is the plus I root 51 over 2, the other is the minus I root 51 over 2. But notice there's no real answers to this problem at all. And graphically we know that that just means that this graph will not touch the x-axis. So maybe the graph looks something like this. You know, it just doesn't touch the x-axis. This happens all the time, right? We have all kinds of examples in our past where we've drawn a parabola above the axis like this. So how many x-intercepts are showing up in this newest picture? How many x-intercepts? Look at the picture. None, right. How many solutions are there to the quadratic? 2. Okay? All right, let's go on to the cubic case. So for the cubic case, you could have a polynomial like x minus 1, x plus 1, x minus 3. You know, you could have that. And it's all nicely factored. Everything's perfectly whole numbers, you know. And you have this graph. Where would it cross the x-axis, by the way? Look at your polynomial there. This is some review. 1, negative 1, and 3, right. Okay, so at 1 and negative 1, and at 3, you would have crossing points. Like that. This is one possibility, you know. Or let's do one in black. How about x minus 1, x minus 1, x minus 3. That's possible. You could have that. What would that look like? Where does it cross the x-axis? Only at 3. right? What happens at x equals 1? That's a touch point, right? See the double multiplicity there. So it looked like this. How many x-intercepts do you see with your eyes? How many red dots? 2, even though there are 3 real solutions. So this still belongs under bullet 1. See? It's the first dot here in red counts as a double. He's a doubler. So that counts as 1, 2, 3 real solutions manifesting itself as 2 x-intercepts. Okay? In fact, we've even seen cubics where all 3 roots are the same. That can happen. So let me show you an example of that. What if it was x minus 1, x minus 1, x minus 1? I know this is very small space. In other words, what if it's just x minus 1 to the third? Didn't you have a flashcard for x cubed? This is just shifted to the right by 1, right? Okay, so this graph is really simple. This graph just passes through 1, like that. So how many x-intercepts do you see? Only 1, at 1, but it counts as a triplet. So it still counts as 3 real solutions. So don't let the number of x-intercepts deceive you. The number of real zeros on a cubic is always 3 or less. Okay, so it's going to be 3 real zeros in all of these pictures I've drawn. Even though it looks like 1 dot, it counts as a triplet. Okay? All right, let's go to the 1 real zero and 2 complex conjugate zeros case. Now this is truly 1 real root, where you have your graph going through the x-axis here, and then any other wiggling it does is off-axis, like that. So this is an example here of the second bullet. And the function might be something like this, x minus 1, that explains why it passes through 1. And then the other root is something that can't be solved, like x squared plus x plus 13, you know, something that gives imaginary garbage. So this is still a cubic. It still has 3 solutions. It's just 2 of them are imaginary garbage from here, and only 1 of them is real. This happens, and graphically, they tend to look like this. 1 crossing point and other wiggles off axis, above the axis or below, you know, up here. So it's not touching the x-axis. Okay, there are many other pictures I could draw. Let me tell you something that cannot be drawn. Okay, this is really important. So I'm going to erase some of this junk. I need to say something about this last drawing I just made. Is it possible for me to make a double root real number and save the last one for an imaginary? For example, can I just do this? Can I say, okay, my roots are going to be 1, 1, and 2i? Is that possible? This is impossible, because 1 is right here, right? If you try to make this a double root, how are you going to draw a cubic through this point? I guess you could draw something like this. But then what does the 2i mean? It means you have wiggles off axis. So it's going to have to go up, back down, and then back up again. It's a cubic. It has to go up in the end. Remember, with cubics, it's 1 arm down, 1 arm up. And the fact that you have 2 turning points here means there should have been 2 imaginaries, not 1. So this is actually an impossible situation. It is absolutely impossible to have 1 imaginary root just standing on its own. That's impossible. If 2i was a root, then negative 2i is automatically going to be a root. Think about the quadratic formula, right? Have you ever solved it? X equals negative 5 plus or minus square root of negative 26 all over 3. Have you ever solved this and gotten 1 answer? That's impossible. The plus or minus dictates that there's 2 answers. It is impossible. So, has anyone ever heard of vacuum polarization? Okay, I'm going off script a little bit here. Let me say something about vacuum polarization. You can research that if you want. Okay, let's go on and talk about the quartic now. So that's 4 powers of x. Okay, so this gets a little more complicated, but you know, you could have a function like x, x minus 1, x minus 2, x minus 3. Or you know, you could have a function that's x, x minus 1, x minus 1, x minus 1. or x, x minus 1, x minus 1, x minus 3. If you plan to keep your roots real, you can play this game all day. All of these would be very simple to sketch, right? But if I shows up at all, it will come with a conjugate partner, okay? So on this next one, if you have x, let's say minus I, which means I is a root, you can be sure that x plus I is right alongside it. They have to come together. So notice, by introducing I as a root, making x minus I as a factor, I had to put in x plus I as a conjugate partner, and that means I lost two roots when I did that. I can't have just one imaginary. If I produce one imaginary, it produces another, and automatically I just lost two roots that are real. On the other hand, if I decide to make, let's say, I and 2I, let's say I want to make I a root, that means I have to make negative I a root. I don't have a choice. And if I want to make 2I a root, I have to put its partner in as well. I've lost all my real roots. I've got 4 roots, they're all imaginary. All of these can be drawn. If you want, you can just draw this stuff. Here's the first one. I drew it with a negative look. It's upside down. But that doesn't matter. So there's your first drawing, for example. The second drawing has a triple root at 1. So it goes like this. So it passes through at 1. That one only appears to have 2 x-intercepts, but it counts as 4 roots. And I won't draw the third one. You can draw it if you want. So I'll just erase it. Just play around with real numbers. And then this next one has a root at 0 and at 1. Any other wiggling it does is off axis. It could have 3 turning points, It's a chord. And the last one, well, you could probably sketch it. It doesn't touch any axis. It has its 3 turning points off axis, like that. Okay, so I'm trying to get you to draw pictures, and now I'd like you to stop and draw the quintic cases. Quintic means 5 degrees. Can you draw an example where you have 5 real roots? Can you draw an example where maybe some of those are double roots or triple roots? Or even all 5 coincide in one point? Play around with it for a few minutes. I want you to practice. Don't forget, with a quintic, you can only have 4 turning points. That means 2 max and 2 min at most. And it's 1 arm down, 1 arm up for these, for sure. Okay, so for the quintic, your job is to draw this for a little while. See if you can draw a couple examples of each case. Sorry about the small space. There's a lot of drawings you could come up with. Just play around with it. Okay, so some examples would include, like my first drawing here has 5 distinct x-intercepts, 1 through 5, they're all real numbers, obviously, because they're touching the x-axis. Here you have 1, in the second picture you have 1 crossing point over here on the left. So this counts as 1 root. I just put a little dot next to it. And then over here on the right you get a touch point, so that must count as 2, see? And then here you have another touch point, so that's another 2. So altogether that's 5, right? 1, 2, 3, 4, 5. That's 5 points altogether. These just coincide. And then this last drawing, I drew a triple root. So this counts as 1, it's a crossing point. This counts as 3, see, and that counts as 1. That's 5 altogether. 5 real solutions, manifesting itself as 3 x-intercepts. If you want to get really creative, you can actually draw this. This is the x to the 5th graph that you memorized a long time ago. How many x-intercepts does it have? One visible one, because all 5 x's, it's x, 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 5 of them, they're all at 0. So there are 5 real roots. They're just all the same number. Manifests as 1 x-intercept. So don't let the x-intercepts confuse you with the degree. You can't really tell what the degree is. You just know that there's 5 real roots here, and they're all 0, evidently. Okay, the next drawing would be that of 3 real zeros only. And what I would draw for that is I would just draw 1, 2, 3, like that, and then do one extra set of turning points above axis or something. That's how I usually draw those. And the last drawing might be something like this. It has 4 turning points, 2 maxes and 2 mins. But most of that stuff just all happens above axis. So we end up with only one crossing point on the x-axis. Okay, so the book has pages and pages and pages of information. But ultimately, I boiled it all down to the following few bullets. Okay, so everybody flip the page. I just put everything into these bullets because honestly, none of this is hard to understand, but it is a fairly tough section to read. So instead of making you read it, let's just go through these rules. The first one is just saying that if you have a degree 1, 2, 3, 4, or something, you're going to have zeros. They might be imaginary, they might be only, like more complex, but they're definitely numbers. There are definitely 5 numbers that solve a quintic. Okay? And there's 10 numbers that solve a 10-degree polynomial. Some of them just have I in them. Okay, the next one is saying, if you know the roots, you can write out the factors. Okay, so if the roots are 2, 5, I, and negative I, then you can write x minus 2, x minus 5, x minus I, and x minus negative I. You can do that. You can always write the factors if you know the roots. That's what the second bullet's saying. You kind of already knew that. Maybe you didn't know you could do that with I. Okay? The third bullet is very, very important. Okay? This is the fundamental theorem of algebra, this third bullet. So circle that one and put a star by it. This is the fundamental theorem. That means you can't live without it. Super important. And it's very, very simple. It just says if you have degree n, you've got n solutions, always. Some of them might be imaginaries. The fourth bullet is saying if a plus bi is a root, then a minus bi is a root. We said that they come in pairs, like the particle and antiparticle, or the 2 shoes on a person's feet. Okay, 2 shoes in a box when you buy shoes. And the last one is very obvious as well. The last bullet is just saying if your function happens to be an x cubed, x to the 5th, x to the 7th, then it's got to cross the x-axis at least once. Okay, and that's because we know that these are basically one arm up, one arm down. So you have to pass through the x-axis somewhere, at least once, to get from the lower quadrants into the upper quadrants. So this is true for any odd. You've got to have at least one crossing point. That's not true for evens though, right? You can draw an x to the 10th that looks like this, and then your x-axis might be down here, see? No x-intercepts, that happens. But with odds, they definitely cross the x-axis. Okay, so there I just saved you like 10 pages of reading. Now let's go to example 1. And I'm sorry your solution's already typed there, but I deleted it on here for the sake of the video. It says a polynomial has degree 5. Okay, so how many solutions is it going to have? 5, that's right. Degree 5 means 5 zeros. Okay, a polynomial f of degree 5 whose coefficients are real numbers has the zeros 2, 3i, and 2 minus I. Find the remaining zeros. Well, they already gave me 3 of the 5 answers. Okay? So, how many are missing? 2. There should be 5 zeros to a degree 5. The conjugate rule says, listen, if 3i is a root, negative 3i has to be a root. And if 2 minus I is a root, 2 plus I is a root. That's the answer. We're done. We found the remaining roots. We're exercising that theorem that says they come in pairs. There's 5. Next example is the same idea. This one's degree 4. So if it's degree 4, then how many zeros is it going to have? 4 zeros. That's the fundamental theorem, right? they told us that they are -4, and there's, oh, and then they told us -2 plus 3i was an answer. That means we're only missing 1. See, they said -4 was a double root, multiplicity too, so I wrote it twice. -4, -2 plus 3i. What's my remaining last root? -2 what? Minus 3i, the conjugate. That's the answer. Those are your 4 roots. So this is just reminding you of that conjugate theorem. Pretty easy. Make sure you have 4 in the end. It's a degree 4. All right, let's go down to these examples here. Okay, now this is where the rubber kind of meets the road and you need to actually solve the problem. Okay? So how are you going to do that? This thing has how many answers? Look at the degree. It's degree 4. We're expecting 4 zeros. Are they all real numbers? Probably not. Okay, so what are we going to do? P's and Q's. Before I do my P's and Q's, I would like to try something. I just want to see what happens if I plug in 0, because I can do that in my head. What happens if you plug in 0? Yeah, more importantly, you get a negative, right? And what happens if you plug in 1? That's not too hard to do in your head. 3 plus 5 plus 25 plus 45 is 78. Minus 18 is what? 60. More importantly, it's positive when I plug in 1. So I plugged in 0, that's easy. That just gives me -18. I plugged in 1, I got 3 plus 5 plus 25 plus 45 minus 18, that's 60. But more importantly, it's positive. What does this tell me?
All your roots keep you on 1.
Not all of them, but there's at least one. One of the answers lives somewhere between 0 and 1. See, the graph cannot cross from down here to up here without crossing the x-axis. We just went from the negative y realm to the positive y realm when we jumped from 0 to 1. And the graphs are continuous, which means it had to pass through somewhere. That's the IVT, the intermediate value theorem. Okay? Really simple. So, I am sure that if I run into any fractions in my P over Q options, I'm going to need them. Okay? So let's do our P's and Q's now. So the P list is 1, 2, 3, 6, 9, and 18. And the Q list is simply 1 and 3. So if you make your P over Q options, you get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. And if you divide by 3, you get 1/3 and 2/3. The rest of this stuff is all redundant. You get like 3/3, 6/3, 9/3, 18/3. That's all redundant stuff. Okay, so these are your distinct P over Q options. And I already decided I was going to try 1/3. I'm going to try 1/3 and 2/3, like right away. Okay? At least I try the 1/3. So let's do our synthetic division. Oh, a quick comment for the advanced learner. You see how this original polynomial only has one sign change in the whole thing? See, it changes from positive to negative right there at the very last instant. Descartes said that means there's only one possible positive answer. So if 1/3 works for me, I'm done trying the positives. Okay? Descartes was a pretty smart guy. Let's try this. I think it actually works. 1/3 times 3. Adding, I get 6. Multiplying, I get 2. Adding, I get 27. Multiplying, I get 9. Adding, I get 54. Yes, sure enough, 1/3 of 54 is 18. Adding, I get 0. So on my very first try, I succeeded. And notice how these are all positive? I'm not trying any more positive choices. There's no sign changes in my quotient. So I'm done. I'm not even going to try 2/3 at all, or 1 or 2, none of that junk. I'm jumping straight into the negative realm for my next step. Okay, I'm going to try -1 real quick. Don't forget you're using your quotient numbers now. But this doesn't work. That was a failure. I got 30. That's okay. Let's try -2. Got to have some failure in life. Okay, so -2.
30 is your remainder, and the remainder of 0 is negative. It wouldn't you find a negative between 0 and -1? The root?
You know, if you want to try to find f of -1, Jack, you little too far the way you stated it. But you're on the right track. If you find f of negative 1 and it comes out to be positive, then you can be sure like negative 1/3 or negative 2/3 works. I was just going to try negative 2. So let's try that out real quick. So this gives me negative 6, 0. This is looking good. Ah, look at that. Okay, so I haven't been working on this problem a whole lot. I've just kind of started, and I'm already getting done because I already know that my answers are, I'll write them at the very top of the board. X equals 1/3 worked out great. Negative 1 didn't work, but negative 2 works. So let's put negative 2 in. And now I'm just left with this little 3x squared plus 0x plus 27. That's not hard to solve. I don't need synthetic division for that. I can just use quadratic formula for this little guy down here. Okay? And actually, if b is 0 like that, you don't even need the quadratic formula. You can just solve it. Yeah, let's just write this. 3x squared plus 27 is set equal to 0. Subtract and divide. It looks like my last two answers are 3i and negative 3i. You know, when you square root this, you get a mandatory plus or minus. Square root of 9 is 3, and square root of negative 9 is 3i, you know. So it looks like my remaining answers are 3i and negative 3i. Like I told you, they come in pairs. This one has two reals and a conjugate pair of imaginaries. Okay, so this would have been a really challenging problem if you didn't know any tricks at all. You'd have had to try maybe up to 16 options here, but by plugging in 0 and 1 at the beginning, we realized there's a fractional answer, so that gave us a head start. 1/3 worked out great. I would have tried 2/3 next if that didn't work. I noticed there's no sign changes in my quotient, so I dished the positive realm and went straight to the negatives. The only failure I had was negative 1. Everything else worked out great. Okay, so try to use some tricks if you can. Let's go to example 4 now. This is our last example. This problem, you can tell, is a little bit harder because they felt obligated to give us one of the answers. How many answers were we expecting on a degree 4? It's a degree 4, so we expect 4 zeros, and they gave us one.
1 minus 3i.
Yes, they gave us a root. Actually, they inadvertently gave us two roots, right? Because if 1 plus 3i is a 0 of the function, then what do we know for sure? 1 minus 3i is also. Okay, so we got 2 for free. We know that 1 plus 3i is given, right? 1 minus 3i, because that's the conjugate theorem. That just leaves us with 2 unknown roots. Okay? 2 unknown roots. Okay, so what you could do is you could make your P and Q list, and you could pursue it that way, and you would eventually stumble across the fact that x equals, I think it's negative 1 works. But I'd like to show you a different way to attack it. You can take your known roots and break down the problem. Okay? So what I'm going to do is I'm going to assume that 1 plus 3i would work if I tried synthetic division. Okay, because they told me it was a root. So I'm going to put 1 plus 3i in the box like this, and then set up my synthetic division. Okay, it's going to be a little bit awkward working with synthetic division using complex numbers like this, you know, imaginaries. But let's give it a try. So first thing I'm going to do is drop down the 1. And I'm going to need to do a little bit of scratch work on the side here. I've got to multiply that by, I've got to multiply the 1 plus 3i times what's written down here. So I'm multiplying 1 times 1 plus 3i. That, of course, is going to be 1 plus 3i. And I'll put that under that negative 7. So I'll put a little 1 plus 3i here. How do you add that to negative 7?
Negative 6 plus 3i.
Yeah, remember, the negative 7 just means negative 7 plus 0i is what it means. So you're grouping like terms. So negative 7 plus 1 is negative 6. And then you've got the 0i and the 3i. So this, what I'm saying is the 3i just kind of goes along for the ride here. It does not combine at all with the negative 7. It's like oil and water, imaginary and real. Okay, now I've got to multiply 1 plus 3i and negative 6 plus 3i. That's awkward. So I'll do that over on the right in blue. I need to multiply 1 plus 3i times negative 6 plus 3i. And if you're very careful and you FOIL this out, you get negative 6 plus 3i minus 18i, so minus 15i. And then plus 9i squared. 9i squared. What does I squared mean? Negative 1, right. So this is really just negative 15 minus 15i. I'll just write a little reminder to you that I squared is negative 1. So there's actually a minus 9 right there. Okay, so that's what goes right here under the 14. Move this over a little bit. Need a little more space. Okay, now I'm going to add the 14 and the negative 15 minus 15i. So what's that add up to? I'm adding straight down now. You can think of this as having a little 0i right there. It's just negative 1, right, minus 15i. Yeah. Okay, so negative 1 minus 15i. Looks like I'm going to have to multiply that by what's over in the box again. So let me erase my old scratch work, do some new scratch work here. So I need to do 1 plus 3i times negative 1 minus 15i. And the FOIL gives me the first is a negative 1. The inner and outer combine to make negative 18i. And then I have a minus 45i squared, also known as a plus 45. So it looks like I'm getting 44 minus 18i. This is awkward, isn't it? Okay, if I add straight down, I get 6 minus 18i. And I already know that this is a root. They told me it was a root, so I already know the remainder is 0, right? And I already know then that this is going to come out to 60. I also tried it earlier. I took 1 plus 3i and negative 6 minus 18i, and I multiplied them. I'll show my work. This is my last little FOIL. This just comes out to 6 plus 18i minus 18i minus 54i squared. But that's just 60. And then this all washes out to 0. Like it should. I mean, it's supposed to come out to be a root, right? Okay, that was really awkward. But it worked. And now I'm going to use those quotient values and do 1 minus 3i. So I'll show my work in red down here. We're going to do 1 minus 3i. And we're going to use the quotient coefficients here. And before you panic, trust me, this one's a lot cleaner. I'm going to pause the... Okay, so that last synthetic division was ugly stuff, but this one's real nice. When you multiply the 1 by the 1 minus 3i, you get 1 minus 3i. Adding, you simply get negative 5. Multiplying, you get negative 5 plus 15i. Adding, you just get negative 6. Multiplying, you get negative 6 plus 18i, which comes out to 0 in the end. So you're left with x squared minus 5x minus 6, which factors beautifully into x minus 6 times x plus 1. This means your remaining two roots are 6 and negative 1. The final answer is in the middle. I'm circling it in black right now. 1 plus 3i was given. 1 minus 3i, that was a freebie from the conjugate. 6 and negative 1 came from the synthetic division. I think you should practice this tonight on number, whatever it is, 25 or whatever. It's about as hard as the math gets. There is another way to avoid doing synthetic division using the imaginaries. So I'm going to show it to you real quick. But the trade-off is you have to use long division. Okay? So let me show you real quick how you could do this problem a little faster, actually, if you're good at long division. So you know that these two are factors. that means that their product is a factor. So in other words, you can just multiply these two together, take x minus the first root times x minus the second root, like this, and FOIL it. I showed you how you can reassociate these. This is x minus 1 minus 3i, and this is x minus 1 plus 3i. I showed you how you can treat this as a difference of squares if you reassociate your parentheses like that. So the FOIL on this becomes just a real simple thing. It's just x squared minus 2x plus 1, that's when you multiply the reds together, minus 9i squared, or you could say plus 9. So this just basically becomes x squared minus 2x plus 10. So what is this thing? This is the product of the first two factors. Now you can take that and do long division into the original polynomial. Nobody really likes long division, but guess what you get? X squared minus 5x minus 6. Which factors? Giving you your last two roots. So this is just like saying, look, if I told you to divide the number 1260 into its prime factors, and I happen to tell you that 2 goes into this, and 3 goes into this, you know that 6 goes in. So you're just basically dividing by 6, and then you're trying to break